recording, and then I'm going to share screen. Okay, so hold on, let me just stop. Otherwise, I cannot get back to the specific page. Okay, so today we will start with a new unit. So it's about model evaluation and hyperparameter tuning. Okay. Okay, admit. So we already learned a number of learning algorithms, is it? But and every here and there, I remember we also discussed some approach to improve the training performance, is it? Like last unit, what we learned is about dimensionality reduction, is it? Because sometimes that can help in regarding to reduce overfit, is it? And we learned like feature selection and the feature reduction, is it? And previously, we also learned, if you recall, that we also learned the regularization, the parameter C, is it? And for the regularization, and if we adjust that parameter C, and we can also avoid overfitting, is it? So those are the topics that every once a while we talked when we discussed about the learning algorithms. We discuss how do we improve the performance. Okay, so today we kind of see overall how do we do the model evaluations to measure its performance, and also about hyperparameter tuning. Okay, parameter tuning. So let's see. And the very first, it's about to streamline workflow with pipeline. Okay, so in SKey, it does have the modules that can help us to do streamline work. So what is this? Okay, if you recall that previously we learned for data pre-processing that, and one part of data pre-processing. So data pre-processing, that's part of your training before you start to do model training, etc. And one of it is to scaling the data, scaling the data. And we learned normalization and standardization, is it, to bring sample data to the same scale, so that when we do SVM or like a gradient descent, is it, then we can make sure that the learning model can be trained with the high performance. So that's data scaling. So that's part of the work. And generally speaking, when you do sklearn, then you need to call fit, and then you need to call transform, is it? So it's two steps. And then we also learned that we can also do dimensionality reduction, that so then over there, you can also call fit and transform, is it? And after that, then you can do learning algorithm, and then you predict the model, is it? So that's the way how individually, is it? For data pre-processing, okay, for feature selection, and then do model training, is it? Of those. And we just said, we can do pipeline way. Okay, so today we are going to see our example. How do we do pipeline so that we don't need for each of this step, we do feed, transform, feed, transform. Okay, so that's the idea about pipeline. So you can streamline the work, streaming the work with pipeline processing. Okay. So that's the first new concept here. And then last class we also learned, previously we learned variance and bias, is it? And do you still remember if your data, so data set, if your data set has a higher bias, normally it will lead to what kind of problem? Anyone remember?
Is it overfitting?
Is it overfitting? So think about it. Okay, higher bias. So higher bias normally leads to underfit. Okay, but can you also send your, you just send higher bias leads to underfit. Okay, you send it to our chat so that I can give you bonus point. Okay, so I remember just someone answered the question. Yeah, even though it's it leads to underfit. Okay, but I can still give you bonus points. So can you send just this high bias? Yeah, leads to underfit. Thank you. Very good. Okay, so higher bias normally leads to underfit, is it? And the higher variance normally leads to what? Who remember? Higher variance leads to what? Who remember? Higher variance leads to overfit. Is it leads to overfit the data set? Is it? Okay, so variance. And what is variance? Variance is what? It's a measure of how far your observed value. Okay, so one of the samples, okay, differ from the average, the mean of the predicted values. That's called variance. Is it? So higher variance, that means spread out too much. Is it? You remember? And also then, do you remember in one of the previous unit, we discussed one approach to deal with dimensionality reduction. Dimensionality reduction, you remember? And over there, we said we choose something that's try to maximize variance. Who remembers what that approach's name regarding dimensionality reduction?
Is it LD, Professor?
Yeah, very good. PCA and LDA. Is it? Very good. You can send your answer to the chat, okay? And try to maximum variance is PCA. Okay, it's a PCA. And LDA is major to, because of a lot of sparse zeros, is it? So that's LDA. So to maximize the variance, is it? It's not maximize, we purpose it's you pick some axis, new axis, is it? Because we are going to do feature space transformation. You remember that's kind of rotation, is it? Rotate the feature space, is it? So you're going to pick some new feature axis, is it? That new feature axis will provide the maximized variance. Is it? So over there, we also discuss variance. And if you recall visually, you remember it's that axis will be along the most spread out one, is it? So that's called variance. Okay, variance. And what the goal is? The goal is if your data set has lower, so the goal is not to have higher variance, okay, be careful. The goal is to have lower variance, okay, lower variance, okay. And the low variance, in studies, there is a score called R2 score can be used to measure it, okay. And R2 score here, it explains, it varies between 0 and 100%, okay. And what is R2 score? It's total variance explained by model over the total variance. So if the R score, so the higher the better. So if the R score is 100%, then that means these two variables perfectly correlated. Is it? So no variance. Is it? Because just think about it. Is it? It's very explained by your model and the total variance. One is your model, one is the real one, is it? And of course, if it is 100%, that means exactly the same, is it? So that's why the higher, and then your model is better, is it? Because you can find some model, is it, that can catch all of the variance, is it? So of course, the higher the better. So it says a low value show low level of correlation, is it? So that means your model may not be valid, is it? But it says not in all cases, is it? And here it also said we also have some other measurements. It's kind of like MSE, is a mean square error. And who remember SSE? What does this S mean? This is SE is still square error, is it? You remember, where do we learn SSE? Previously, in previous units, we learned kind of toward the beginning part. SSE is what? Is sum of the squared
error.
Yeah, very good. You can put your your answer to the chat. Okay, so that I will issue you bonus point. So sum of the square error. Okay, so that's also, and sum of this is mean square. Previously, we learned sum of the square error is about what? Is about the weights, is it? And we try to minimize it. And we have that's basically the starting point of machine learning, is it? When we learn machine learning, it's gradient descent, is it? That's a very important concept, okay, gradient descent. Okay, gradient descent. You remember that contour, the lowest point, is it? And how do we find the optimized point? Is it we approach, gradient, because that's the foundation of neural network, is it? And the neural network also contribute a lot for deep learning, is it? So that's why let's get that gradient descent concept. Keep that in mind. Okay, so that's the bias and the variance. So here we discuss is we try to find some trade-off. Okay, so what does that mean? So let's take a look. Okay, so here we have this trade-off discussion. Okay, so what's the best? So this is kind of like some target, is it? And here's, you try to minimize mean square error by minimize both the variance and the bias of the model. Okay, the model. So the central part, this central part is what's the real scenario, is it? The real scenario. And then like we want to approach to the center, is it? As close as possible, is it? But it depends on how your data is distributed, is it? So the first case is you have low bias and low variance, is it? So low variance means the data set kind of concentrated. Is it concentrated? It's not spread out that much, is it? And the low bias means it's not off. It's not off what the real performance should be too much, is it? So this is the perfect scenario, is it? All of those dots means data set. The data sets are kind of very close to the center of the target, is it? And they are all kind of grouped together very tightly, is it? So that means it has a low variance and a low bias, is it? And okay, next let's see this case. It's a low bias and a high variance, is it? Yeah, we can see the data distributed, is it? It's spread out a lot compared with the this left diagram. Is it spread out much more? Is it? But it's not go all the way to the outer yet. Is it? It's not. It's still kind of close to the center. Is it? That's why, because it's still close to center. Is it? But spread out more. That's why we say it's a high variance and a low bias, is it? And then let's see this case. This case is you have low variance. Yeah, it is it? Because the data not spread out that much. Not spread out, is it? It's tightly closed, is it? But off center a lot, is it? So that's why we say it's a higher variance, but low or higher bias, but with low variance, is it? And this is the worst scenario, is that you have a higher variance and a higher bias, is it? So it's off center a lot and also spread out, is it? A lot, is it? So that's the worst scenario, is it? Okay, so here it gave us all sorts of scenarios. So that's why we said we needed to find a model that will trade off, will balance between the bias and the variance relationship. So that's the goal, okay. And then next, let's see. Okay, how do we, so we can see this diagram visually that help us understand a lot. Is it? And normally high bias can be caused by what? If your model is too simple. Is too simple. Is it assuming like your model should be a polynomial model, but you use linear regression, then of course the model's accuracy will be low. Is it? It will be low. So that means your model is too simple. Is it? So if you increase complexity, then that will bring the bias arrow down. Is it? That's why this, that's what this curve shows. Is it? With the increasing of the model complexity, is it? The arrow will be dropped. Is it? Arrow will be dropped. So that's, we understand this. Is it? That's regarding model complexity and arrow relationship, then that can be reflected for our bias. Okay. And next, let's see the variance. Is it? The variance is the opposite way. Is it? So this is the curve, the variance. The variance is the more complex of your model, is it? The higher the variance it's going to be. And the why? You remember previously we said, is it? And if you use a super polynomial model, is it? To fit, because what are you trying to do with your model? With model is you use training data set. You use your training data set to fit the model, is it? Fit the model very well. Very well, is it? But the accuracy drops, is it? For predicted data sample. Is it? That means your model only fits with the provided data set. When there is a new data comes, that cannot reflect well. Is it? So that means you have a higher variance. So one of the reasons is your model may be too complex. Your model catch too much of the noise for the training data set. And so it doesn't reflect well for predicted data. Is that for predict? So you can see it's opposite way of the bias. Is it? So what's the best scenario then? So what's our goal? The goal is you need to find what? Find the minimized. We try to minimize the error. So you pick a model, is it? So this is the model you picked. And with this, you picked the model. So this part is the arrow of variance, is it? Arrow due to variance. And this part The red part, is it? It's error due to bias. Is it due to bias? And this is some model that you picked. Is it? Some model you picked. And then you add both of them together. You add both of them, and this will be the minimum sum of the error due to bias and variance. Then this is the best model that you can find, okay, with the provided data set. So that's what we call the trade-off. So we are going to find the optimum model complexity. And then you don't want your model too simple. Also, you don't want your model too complex. You need to find a bargain point that will minimize the summation of the error due to contributed from bias and from variance. Okay, that's our goal, okay? So this, we call it bias and variance trade-off, okay? Okay, and the bias variance trade-off, how do we do it? Is it so when we to achieve the goal? Previously, we also learned, if you recall, in our example, cross-validation. Okay, so cross-validation can help us do that. So cross-validation is, previously we learned, is it whenever you have a data set, and we are going to do split. We just split into two parts. Is it training data set and what? And the testing data set. Is it? And with cross-validation, then for the data set, is it? We also add what? Validation. Is it? So basically over here, you're going to subdivide into training and validation. Validation. Is it? So we have kind of three sets. Is it? As previously, we also learned, we use a k-fold cross-validation. Validation. Is it? Yeah. So that's one way to try to find the bargain point, okay, the trade-off between variance and bias, okay, because like over here says validation set, then used for model selection, is it? Because you try to find the best model, is it? Okay, so this is the idea about how do we achieve the trade-off between bias and variance, okay? And you remember previously we learned the cross-validation, as you have training set, and then you subdivide into training and validation. But previously we learned, this is called hold off. You just have one set, but there is a problem with the hold off cross validation is too sensitive, how we partition the training is that data set. So that's why later on we said we use the k-fold cross validation as a k-fold cross validation. If you recall, is it? That's for your training part. So this is your training part of data set, is it? Then you have, so you divide it, we call k-fold. Is it divided into number of folds? In this case, generally speaking, it says good standard for k-fold is 10. Is it? So you divide the original training set into another 10 folds. Is it? And then you have 10 iterations, Be careful, okay? It's just not one iteration. It will be done in 10 iterations, is it? And each iteration, you will leave one fold out for validation, is it? And then you take the mean of all of the iterations, is it? That's called k-fold cross validation, okay? So the goal is to balance bias and variance, okay? And we already learned, is it previous? So here's just a quick review. Okay, the next one is a new concept, okay? So to help us we call it diagnosis tools to improve the performance of our learning model, okay? So here we have a new concept, learning curve and the validation curve. Okay, so what are those? Okay, so the first one is about learning curve concept, okay. Here it says if model, generally speaking, if model is too complex, it can lead to what problem? Can lead to what issue? Who remember that? Generally speaking, if your model is too complex, you recall that curve previously we drawed regarding variance and bias. Do you remember? Here we have the arrow, is it? And here we have the model complexity. Is it, you remember? We have this curve and this curve. Do you remember? And this is regarding what? This is regarding what? Previously, we discussed this is regarding bias, is it? And the other one is regarding variance, is it? And if the model is too complex, it will lead to what? High variance, is it? Variance is going to be increased. If variance increase, it will lead to what? With the increasing of variance, what it will lead to? It will lead to overfit. Now, keep all of this in mind, okay? Okay, it will lead to overfit, is it? And they said that because too many degree of freedom or parameters, is it tend to overfit the training. And why is variance too high, then it will overfit the training, because it will not generalize well to unseen data. And so you just try to meet the pattern of the existing data, is it? But your future sample, your future predicted data, it may be off your model, is it? So it will not generalize well, is it? So that's why it can cause overfit, okay? And one way to approach is that you can collect more training sample, is it, to reduce the degree of overfitting, is it? But in realistic, it may be more expensive, is it, to collect more data, is it? So there is a way. Here we set a curve, is it? So we can plot the model training and validation accuracy, okay, versus training data size. So that's regarding learning curve and validation curve, okay. Then it said it can help us detect if the model is overfit or underfit, if it has higher variance or higher bias, okay. So learning curve. So learning curve is about what? is about accuracy versus, so if we have the coordinates, so accuracy is the y-axis, and here is your data size, data set size, training data size, is it? And you want a certain desired accuracy, is it? And if your accuracy getting close to this desired accuracy, then that's a good model, is it? So that's what we call learning curve, okay? Okay, so here let's see. The diagnosis, bias, and variance problem with learning curve. So basically we try to solve the issues of overfit and underfit. Is it? So higher bias or higher variance, it can cause underfit or overfit, is it? So let's see. So the first scenario, this is number of training samples, is it? And the y-axis is the accuracy, And this is the desired accuracy. So suppose 95%, 90% or something, is it? And of course, you see, this is training accuracy curve. Okay, and this is validation. So training, this is for validation. And you can see both training and the validation, no matter with the increase of the training samples, their accuracy of the desired accuracy a lot, is it? Of a lot, is it? And it also looks like the training accuracy is decreasing and the validation is increasing in this case. But no matter what, both off a lot with the desired accuracy, is it? So that is caused by higher bias. Is it? Higher bias may be caused by what? May be caused by your model is too simple, or you have too fewer data set, training data set. Is it? That can cause a higher bias. Is it? Okay, then let's take a look at this scenario. In this scenario, so this is desired accuracy, is it? And with training, it fits quite well, looks like, is it? So this is training. So training accuracy higher than desired accuracy, is it? But validation, you can see, in this case, is validation accuracy is lower than the desired accuracy, is it? And of course, this caused overfit. That's what we call overfit, is it? And overfit is caused by higher variance, is it? So if you see we train our models, is it? And we can then plot this kind of diagram, then it can help us to understand if our training model is good or not, is it? And the best is this scenario, is the best trade-off, is it? So both your training accuracy and your validation accuracy approach to each other and as well to the desired accuracy, is it? So then in this case, you have the bias and variance trade-off balanced very well. Okay, so that's regarding the balance of variance and bias. Okay, and with the learning curve, we already discussed that. Okay, so visually, so it's kind of, so let's see. So there are some approaches, basically, we already discussed, is it? So higher bias lead underfit, we already know, is it? And the reason for higher bias, for underfit, is maybe your model is too simple. Model simple means what? Means the number of parameter of the model may not be enough. Is this so you can increase? Is this? It's just like you change your model from linear regression to polynomial regression. Is it? And you can also add more feature. Is it? Add more feature. We can also do what? Decrease the degree of regularization. Is it? You remember in SVM and logistic regression, classify. Is it? You can decrease the regularization. Is it? Because you decrease the regularization. Is it? It will adjust better for the weights. Is it? That will contribute better to the SVM or logistic regression. Is it? So here's basically all of those approaches in previous chapter we discussed, and then we just not to summarize them. And for higher variance, it causes overfit, as we already know. Is that one approach is to solve the issue is you can collect more training data, as in more training data. And we can also do dimensionality reduction, as they reduce the complexity of the model. We can also increase the regularization parameter. Is it? Increase the regularization parameter for one case is what? Is that C, is it? And the C is for the lambda, is it? Ingredient descent, is it? And the basic is that lambda, you remember it's I is a WI square, is it? Or you do this WI, is it? So this is L2 regularization, is it? And we also have L1 regularization, is it? And the purpose for this is to what? Because that's try to your cost function, is it? You try to minimize the weight, is it? And if you decrease, because C and the relationship of that lambda is the inverse of the lambda, is it? So if you decrease C, you increase the lambda, is it? You increase lambda, that means you increase the contribution of the penalty terms. Is it penalty terms? And the penalty what? It's penalized weight. Penalized weight. Is it? If you penalize the weight, of course, you're going to reduce certain weights' impact. Is it? For L2, it's reduce the weight value. For L1, then it may even bring some of the weights to zero. Is it? That's why we said L1 can also contribute to what? To feature selection. Is it? Yeah, so that's what we discussed. You can also through the regularization to adjust the variance, is it? So that's previously we already learned of this, is it? We just didn't summarize the relationship, is it? Okay, so that's about a learning curve, okay, learning curve. And here it says we can also use a validation curve. So similar, is it? Then validation curve is over the x-axis is size of the data set, training data set, okay. Training data set, is it? And the y-axis is what? Is validation accuracy. Is it? The accuracy. Okay, so we can also plot this curve, okay, to help us, because the validation's goal is to help us select the best model, is it? So then in this case, we can verify the values of the model parameter. Oh, I'm sorry. I'm sorry, that's not about the size of this. I got messed up. It's not a size, it's the parameters over here. Validation is regarding parameters. Okay, so parameter value change, parameters value change. Okay, it's regarding x-axis, and then the y-axis is about the accuracy. Okay, the model's accuracy. Okay, I'm sorry, I got that concept wrong. That's a learning curve. So validation curve. Okay, so you vary the value of the model parameter. Is it, for example, that C? Is it you can pick different C value? Is it, and then you can get the accuracy. Then we can analyze. Okay, so that's about validation curve. Okay, and another new approach in sklearn, it provides us, it's called a grade search. Okay, so we don't need to do one by one ourselves. Okay, the grade search kind of provide a combined approach to help us to fine tune our model. Okay, and in machine learning, it says we are two types parameter. There are two types of parameter, and one type of parameter is like the weight. Is it in logistic regression? Is it gradient descent? Is it we always try to adjust the weights? Is it? So that's one type of parameter. The other type of parameter is like the regularization. Is it parameter? Is it that parameter? We call it hyperparameter. Okay, so hyperparameter, be careful. It's not about weights, okay? It's about the parameters in your model, okay? You can adjust, like over here says depth of the decision tree, okay? So it includes like the regularization, parameter C, is it in sklearn, we use C, is it? And like the depth of decision tree, is it? And the number of trees in random forest, those kind of parameter, they are called a hyperparameter. Okay, so approach, okay, so it's a popular approach to help us to tune that, to optimize, to achieve the optimization of a hyperparameter is called grade search. Okay, grade search. And we will see that in our example about the detailed information, how to do it, okay. And there is another approach that can help us improve the overall performance, is called nested cross validation. Okay, nested cross validation. For nested cross validation, It says the outer k-fold cross-validation loop, okay, is to do is split data into training and data set, is it? And an inner loop used to select the model also use k-fold cross-validation on the training fold. Okay, on the training fold, be careful, okay. And after you select the model, so basically it says, because this is nested cross-validation, is it? So the inner loop will do what? Will help you do model selection. Is it? That's for the inner loop. And the outer loop, we do what? So after model selection says test fold, then is used to evaluate the model performance. Okay, that's what nested cross-validation does, okay. And we can see this diagram, is it? So we have the k-fold, is it k-fold? And you can see within the training fold, over here it shows, is it? Within the training fold, then you further divide into training fold and the validation fold, is it? And within this inner loop, this inner loop can help us to tune the parameter, is it? To tune the parameter, okay? And the outer loop does what? It to train with optimal parameter, okay, to evaluate the model performance, is it? So with this nested cross-validation, then we can do much better, okay? So, and the recall precision, is it we already learned, is it confusion matrix, is it previously we learned that. And a related concept with the true positive rate, so this represent true positive rate, is it? And this represent false positive rate. Is it? That's previously we discussed about precision definition, is it? And recall, is it? And we also have an F1 score, is it? Previously we learned when we discuss a model's performance, a lot of time we use the accuracy score. And then we use accuracy score, but accuracy is not the only measure you are going to measure performance, is it? And we also have precision, recall, F1 score, is it? We go to detail about the true positive, false positive, those definition, is it? And there is some graph, okay, it's called ROC graph. What is ROC graph? It's a receiver operating characteristic graph. It says this graph is also a useful tool to select a model for classification. Okay, it's used what? It's used the true positive rate and the false positive rate, okay, to select the model. So this can also help us, okay. And then it says within that graph, okay, and then later on we will see the diagonal one, okay. The diagonal one of that graph is basically just a random guessing one. So we should pursue, if your model is fall below the diagonal, that's not a good one, because that's even worse than random guessing, is it? So the good model is that ROC curve should be above the diagonal curve, okay? And the perfect classification is what? Is going to be at the top left corner of the graph, okay, with true positive almost 1 and the false positive rate almost 0, okay, almost 0. And here it also say, with that curve, we can also find the area under the curve. So AUC, okay, area under the curve. So the larger of that area, the better of the model. Okay, so that's the concept. Okay, so the concept part is almost done. Okay, for this new unit, and tomorrow we are going to discuss the example. And sorry, I'm kind of getting too late. So I'm going to just quit today's class. So that's it. Okay, bye. See you tomorrow.